Should be going up live now.
Then
Once that's done, share.
yeah, and then cool. If you could just start projecting the slides, and I got started.
Just started. Just triple checking stuff. Give me a minute. Okay. Okay. Oh, yeah, thanks.
All right. Thanks, everyone. So, a little bit of a delay, but we'll get started in that case. So, we don't take up any more time. Thanks for coming along to Systems of Vision workshop for model computation. We'll just speak to the next few slides and we'll get straight into it. So, just a quick disclaimer before we get into anything else. We're required to say that we cannot guarantee that anything on this revision workshop is guaranteed to be in the exam, or that's necessarily indicative of it. That being said, we have worked rather hard to make sure that it does align with the current curriculum and have gone through all the processes to make sure we're not misleading you in any way. But just to be very clear, we're not guaranteeing that anything that we'll show here will be on the exam. So, real quickly, system revision workshops are run every single semester, covering as many subjects as we can try to cover, and try to provide the most amount of value to the most amount of people, giving you a quick summary of the entire course curriculum. We aim to try to unite the entire community, which can often feel a bit fragmented at times, which seems on this slide. They're run by CISA, basically one of the three community associations at the University of Melbourne, which runs social events, industry events, upskilling events, education events, and provides a variety of other services to the University of Melbourne student community. If you're interested, we'll give you like 5 seconds to scan our link tree up here, your QR code. If not, that's okay. We'll have something on it at the very end as well. That takes you to all of our resources and events overall. In that case, let's get to the next slide. That's by our lovely tutors here today, who have volunteered their time not only to update our content, but also to present. This slide didn't show up, but I'd also like to make an acknowledgement of country, noting that the land that we are currently working, studying, and living upon is that of the unceded Wiradjuri people of the Kulin Nation, among any other First Nation communities that we acknowledge their elders or past present and emerging. Alright, with that in mind, I will wish to take it away. Thank you. Alright, so I'm going to be presenting the first part of the course, which is about the logic topic. So hopefully you remember a little bit of that. I know it was a long time ago, but we'll just start with a little bit of a warm-up, so some pretty easy exercises just so that you can kind of remember what the different logic types that we learned about are. But I think the bulk of this first part of the session is going to be going through some detailed examples of the resolution, refutation proofs. So next slide, please. So we looked at 2 main types of logic in this course. So the first one, if you remember, was propositional logic. So that was the one that had all these propositional letters, we had the connectives, right? And we had those truth assignments, truth tables here. And then in the second half, in the second half of the course, we looked at predicate logic. So that was kind of building on what we did a little bit more complicated, right? So we introduced those quantifiers, predicate functions, things like that, and we had the interpretation function, the universe, things like that. So let's just get do a little bit of a warm-up exercise, just so you can remember exactly what these are. There's just some very simple statements. Let's try to translate these into propositional logic first. So, yeah, part of that is going to be defining the propositional letters. I think that makes sense. I'll just give you like maybe 1 minute to do that.
don't need to be silent either. We can. Okay, would anyone like to volunteer? What are some propositional letters that we might want to define here?
ENS.
Sure. ENS, and what are those stand for?
External number.
Yeah, great, exactly. So what would be a translation of the first? Well, so remember we're doing propositional logic first. So those quantifiers come later. Right? So for now we just have those letters. Propositional letters.
Nobody said anything yet. Nobody said anything.
E implies X.
Yeah, exactly, right? And what about two?
I'm sorry.
Yeah, and then the third one, what about the third one? Okay, so which of the above three statements are logically equivalent? Not quite 2 and 3, right? So if today is a Sunday, then it is Easter. If today is not a Sunday, then it is not Easter.
Is it 1?
Yeah, 1 and 3, right? So maybe let's move to the next slide. So that's the functional positive. Hopefully you remember what that is exactly. You can kind of think about this. Imagine when we have that implication, we can replace it with not and then or. So if you think of the first one, that's equivalent to not E or S. And then the second one is not S or not E, right? So those, you can see how those two are. So next slide, please. Okay, so now we're going to do the same thing, but this time we're going to use predicate logic. So I think that's what you were doing before. So we'll just quickly, I'll give you 30 more seconds. Let's just translate the same statements, but this time we're going to use predicate logic. And I want you to also think about what would be a reasonable universe and what's a reasonable interpretation function.
Thank you.
Anyone have a reasonable universe just off the top of their head? What would make sense?
Days?
Yeah, like calendar days, right? That would make sense. Okay. Okay, so maybe let's just move to the next slide. So these were pretty much very similar to the previous ones, right? So our universe could be calendar days, and then we would define these predicates. E of x means x is Easter, S of x is a Sunday, right? And then it's just relating those three statements back. So now we have this quantifier, right? We're saying some sort of general rule, right? If today is Easter, then today is a Sunday, right? So for all calendar days, if it's Easter, then it's a Sunday. Okay, so let's move to the next slide. So a main kind of topic that we did in this logic section was doing kind of all these different steps to prove something using resolution. So just as a reminder, what do we do in a resolution replication proof? So we want to show that if the set of formula is true, then a given conclusion is true. And the way that we do that is using a proof by calculation. Okay, so how do we do that in the different logic that we looked at? So in propositional logic, we have these kind of 4 or 5 shorter steps. So the first thing that we're going to do is we're going to try to convert all of our statements into CNF. So do you remember what that is? Okay. So the first thing we're going to do is we're going to eliminate those computations. Right? We're going to push the negation through and use those distributive laws to obtain CNF. And then from there we can do resolution. And hopefully do that. In predicate logic, it's a little bit more complicated. So some of the steps are the same. So we still want to eliminate those implication symbols. We want to push negations through. But then we have to deal with things like shadow variables. We want to make sure that the variables that we use kind of make sense. We don't want to have two of the same one. Right? We have this notion of scholomizing things, which we'll come back to in the detail example. We have clausal form. And then when we're drawing the resolution tree, we have unification, right? So this is just to help you remember a little bit of what we did. So maybe let's move to the next slide. Okay. So we're going to go through this detailed example, and I hope that by going through this example, it will refresh your memory and make you feel a little bit more confident for any question you could get on the exam. So let's begin by just giving you a little bit of context. So the problem that we're going to be looking at today is to do with real numbers. So let's just imagine some collection of real numbers, and I'm going to call that A. So in this diagram, I've written A, it's completely arbitrary, but I've just drawn it as this blue set here. Okay, so what do we know about A? Well, I'm going to say that A is bounded above if there is some number B, so that's this black B here, that is not smaller than every element in A. So what does that mean? Well, you can see here, right, this B is greater than or equal to everything in A. That kind of makes sense. So with that in mind, I want to translate this sentence, A is bounded above, into predicate logic. So A is bounded above was this sentence. And you can use those predicates there that I've given you. So A of X means X is an element of A. And L of XY means X is less than or equal to Y. So now we're making it a little bit more complicated from the warm-up exercises that we did. So maybe I'll give you around 2 minutes to try and do this translation. And then we'll come back and see what we do. Feel free to discuss amongst yourselves. We don't need to be beside
Thank you. That'd be really appreciated. But yeah, I'm gonna start taking notes today. I'm gonna do start taking the notes and stuff about today because I have to do feedback stuff. Also, I need to go around and check where the last screen sheet is. I need to go around and check where the last screen sheet is. Sorry, what's wireless? Oh yeah, I could. It's just, it only goes forward. Yeah. Oh, well, if you want to, oh, you can use the mouse wheel.
We've seen how you have it.
Okay, great. Thank you.
I'm gonna go.
Awesome. Appreciate it.
Okay, what do we think? Are we finished? Do we want a little bit more time? Does anyone want to share their solution?
Is it so for all x, A of x implies L x?
Yeah, so that's kind of the general idea, right? I think you also want to add that existential quantifier as well. So we say that A is bounded above, right? If there is a number B, so if there exists some sort of Y, right? If there exists some sort of Y such that for all x, right, if x is an element of A, so A of x implies that x is also Y. So that's pretty much what you said, but instead of using the constant B, we're just going to use the existential quantifier. Is everyone happy with that? Yeah? think something to point out here is it's really important that you get the order of the quantifiers right. So here, we're saying that there is one number that is greater than or equal to everything in A. But if you were to swap the quantifiers and you said, for all x there exists y, right? You're just saying that each element in x has some number that's greater than or equal to it, right? And it could just be the number itself. So it's not really saying anything. So it's really important to get the order of these quantifiers correct. Okay, so now let's make it a little bit more difficult. So I want you to translate these 3 sentences, and we're going to go through it. It's not as scary as it looks. But we're going to define some more predicates. So let's define u of x. So u of x is going to mean x is an upper bound for a. It's a little bit different to what we talked about before. So we're going to say a number is an upper bound for a if and only if it is as large or larger than each element in A. So now we're saying basically that in this example here, B is going to be an upper bound for A. And why is that? It's because every element of A, so everything in this blue set, is as small or smaller than B. Okay? So it's an upper bound if it is as large or larger than every element of A. Okay? And then we're going to define, so maybe let's just do number 1 for now, and then we can come back and talk about number 2 and 3.
There would be, but we're currently having, still discussing with Ben to set up like a public folder for the viewing slides because we don't want it to get added in and stuff. So by the end of tonight, I should upload everything from FSC all the way to SMD and log. Because I've definitely been finding that as an issue in terms of like, every time we have slides, right? The only way we can have it public viewable without it editing is through Canva. It does, but actually no, that's actually a great idea. Now I think about it. Actually no, I'll do that. I think the biggest thing is like whenever we host pieces, you can't get access to this folder unless you're part of the system. Like as in you have this account, so nobody else who has the student accounts would be able to access it. So I'd have to hold it personally on like my Gmail or like
Yeah, I'm not sure. I'm looking to share options.
Okay, so does anyone have an idea for this one? We still need to think a little bit longer.
Can we say
there exists a y for all x such that a of x and a of y and L of x y implies u of x?
So it's a little bit different to what I had here. So I guess the first thing to notice here is that we're making a statement about numbers. Okay? We're saying that a number is upper bound. Whereas before, so here, we were talking about A is bounded above. So A is bounded above. I know that there exists something which is upper bound. But here we're kind of defining what it means to be upper bound. So here we're going to use a universal quantifier. Right? So for all numbers y is an upper bound. So hopefully you can kind of read off the translation here. So y is an upper bound if and only if for all x. If x is an element of A, then x is the sum of y. Right, so let's try to read off the translation from here. So a number is an upper bound for A, so that's just for all y, u of y. And that's what u of y means. If and only if, this y is if and only if it is as large or larger than each element of A. And that kind of goes back to what we did a few slides ago. So if it's as large or larger than each element of A, well, that just means that every element A is less than or equal to Does that kind of make sense? Okay, great. So now let's go back. And let's try number 2.
So now we know what it means to be upper bound.
So that's these kind of these things like that. Something that's bigger than or equal to everything in that set. Okay. So now let's introduce this concept of a least upper bound. So what's the least upper bound? Well, it's just something that's an upper bound and it's the least one, right? So if I look at everything that's an upper bound, so if I look at all of these v's, all these possible v's here, right? It's the smallest one. So what does that mean? Well, it means it's an upper bound, and if I look at every other upper bound, it is as small or smaller than. So to translate this statement, we're going to need a little bit more, a few more predicates. So one of those is going to be this S of x. So S of x is just going to be x is the least upper bound. So let's have a go at translating number two. It's going to be a similar name as the first one. So we're kind of focusing on this idea of what is the number going to be the least upper bound. So you're going to start with your exponential quantifier. For all x, S of x, something something. So why don't you try to fill in what the remainder of the calculation is? So in this picture, right, I've just drawn in this S to give you a little bit of a visual understanding of what we're talking about here. So B is going to be an upper bound of the least set, right? Because it's all the way over there. It's true that B is greater than or equal to everything in A. But you can tell that that's also true for S, right? S is here. S is greater than all of these. But also S is less than or equal. So S is going to be the lowest of these possible items.
They can. It's really bad.
Hey guys, can you guys hear me? Hello?
Okay, so maybe I'll give you a we have a predicate that means x is the upper bound for a. So we don't actually need to use that. So if you're thinking about say for all x is a, like that, you don't need to do that. We're only looking at this concept of upper bound. So we don't need to have like three different variables. It's actually relatively straightforward. I know it's a little bit scary, all the kind of and stuff, but maybe let's try to hone in on what the words actually. So does anyone have any? What do you want to propose to do? Yeah. For all payments, if instead
implies u of x, and for all y, if u of y, that implies L of x. Right?
Yeah, exactly. That's exactly right. So let's follow that. Right. So again, we can just directly map the phrases, the English words, into the translation. So if a number is at least up or down, so for all z, s of z implies, then it is an upper bound for a, right? So that's u of z. And also, it is as smaller than every upper bound. So every upper bound, so for all y, and that is what. So we're just taking one English and just writing directly. Any questions? Let's try number 3. So number 3, maybe a little bit less complex. So x is less than or equal to y, and y is less than or equal to x. If that will be x plus y. So now we need to use this additional, that should be a we have p of x, y, which is x. There's a bit of abuse of notation here. So first of all, what quantifier is this? Right? Because of all our numbers. So first step would be having numbers to quantify. Any suggestions on the
Full X, full Y, L X, Y. That's Y,
exactly. So okay. For all x and for all y, x goes to y, and y is equal to x. Okay. Okay. So now the next step in our resolution.
Okay, question let's say, I think that E implies S same as not E implies not.
No, so that not as the one.
Oh,
Okay. So the next step in our resolution replication process is going to be converting these formula into causal form. So just because if we kind of do everything at the end, it's going to get too long. Let's just split it up into parts and we'll practice converting these into causal form for each of those 3 statements that we just got earlier. So I'll give you probably 5 minutes to go through and do that. This is just the same process that you would have done in your Windows. Yeah. Yeah.
and, you know,
Okay, I think this audio should be better.
No, perfect. I did.
Okay.
Yeah, I used to, so I wasn't so. Yeah,
Okay, how are we going with the conversions? Do we still remember how to do it? Yeah. So I guess the first step for this one would be we replace the by implication with what do we do exactly? Does anyone remember what we do? Yeah, exactly, right. So you'd split it up into the two implications. Yeah. And then how do we convert just a one-way implication? What do we do for that one?
A or B.
Yeah, exactly. Yeah. Okay, should we go through the first example? Okay. So the first thing we do, right, is we're going to split that by implication into two implications. Right? So all we've done is we just split up the by implication one way and then the other way. Okay, so then the next step is we're going to turn all those implications into not or, like you said. Right? So we turn it into not or, and then we need to bring through those negations. Okay. Bring through the negations. And what have I done here? I've just renamed this to be Z to be a bit clearer because we already have an X over there. Okay. So do a bit more rearranging. And now we have a there exists kind of thing. Right? So when we're converting it into clausal form, we need to do this process called scolomization. Hopefully you remember what that is. There is just one subtlety here, which is that this for all y, right? For all y applies to the entire expression, including the there exists z. So what does that mean? It means that our z is allowed to depend on y. So when we're doing a scolomization process, we need to turn it into a scolom function. I think this may not be accessible for you, but I know you probably would have gone through it during the lectures this semester, but I'm not sure if this is actually accessible for you. Okay, so now we have a nice form.
Where does existential quantifier come from?
It comes from moving the negation through the universal quantifier. So that's this slide here. We're moving the negation through. So the for all x becomes, a there exists x, and then it's just renamed it in that step. Right. That makes sense? Okay. So now we can turn that into causal form. Right. And now just to be on the safe side, I'm just going to rename all the variables in there as well. All right, so I'll just rename everything just to make it nice and clear when we go to do the resolution. Okay. Okay. Yeah. When is a good time to scolamize? Let's go back to this kind of procedure that you were taught. So a good time to scolamize is, I guess, before you do the distribution, right? Before you drop the universal quantifiers, because you still need to know, is this existential quantifier, does it come after the universal ones or does it come before? But after you push the negations through, because you need to push the negations through to know if you actually have a existential universal quantifier. Yeah, yeah, exactly. Okay, any other questions? Yeah.
Really better. So if we go where we start, we have the full X there on the right of five equation. But on the left, we've done having
We have, what was that, sorry?
Here on the X's, but I seem to recall there was some rules like we don't have any parentheses in it. think you can take out the full length of
I'm sure that this procedure is not going to be unique, right? You can do different things. I'm not entirely sure what you're referring to, but there's many different ways to obtain the clausal form. You can do, various different procedures. It's not going to be unique. This is just one way that you could do it. Does that make sense? So the for all x is on the right-hand side of the by implication, right? So I think maybe what you're confused about is why we have a for all x here. Is that what you're confused about, or?
Yeah.
Okay, great. Okay, so now let's go back to the examples. How are we progressing with doing the other two? Maybe I'll give you a bit more time to work on those as well. We will probably have to pick up the pace a little bit though. So I'll maybe give you 2 more minutes to do those, and then we'll just go through and start working on some resolution. So if you want, I can go back to those steps that we looked at. Yeah.
I think what he was trying to say earlier was in some of the lectures, there was at some point a distinction made between circumstances where you need to rename the same variable at another part of the equation for some kind of clarity, and other situations where you don't rename it, you keep the name the same. I think that's what he was going to say. Yeah.
Yes, so right. So in this example, I think you'd always want to rename it when you have like a for all x, and then within that for all x, you have some other quantifier that also uses x, and it's kind of like overlapping each other because that's a really confusing situation. But here we don't really have that until a bit later on when we have like a there exists. I mean, you can always rename stuff, it's fine. I would always err on the side of renaming things. I mean, you can't just like rename half of the y's as another thing, right? You have to be consistent. But in this case, yeah, it's fine. Okay, we might just have to go through the other two very quickly. I might just show you what we get, because then we can move on to doing some resolution. Okay, so we looked at that. So here's the next one, right? A similar procedure. We turn the implications into not or. Same process all the way down. We end up with this clausal form. Okay, and following the same process for the next one as well. Okay. Okay. So now I want to talk about some of the things that we're going to prove using resolution. So the reason that I chose something maybe a little bit more complex is so we can actually prove something interesting. So the first thing that we're going to think about proving is this idea of uniqueness. So the least upper bound is going to be unique. So what's kind of the intuition for that? Well, I've drawn another diagram here, right? So if b and b prime are least upper bounds, what does that mean? It means they're less than or equal to every other upper bound, right? Well, it doesn't really make sense for there to be two distinct upper bounds that satisfy that property, because one of them would be bigger than the other, right? And then it wouldn't be the smallest one. So this kind of makes sense intuitively. But now the question becomes, how do we actually prove that using resolution and using the techniques that we've learned this semester? So I'll put up the clauses that we just derived. So these are the clauses that we showed in the previous steps. So now what I want you to do is I want you to take this statement right? And you're gonna have to transform it in some way. You're gonna have to translate it, right? And then you're gonna use these clauses and whatever you do to this statement to do a resolution proof. So do we remember the process of doing that? Maybe I can go back to the steps that we looked at before, right? But we're gonna do a proof by contradiction, right? So what would I have to do to this statement? I want to prove it using resolution refutation. Do I just leave it the same and then just add the clauses on and then do resolution, or what do I have to do to the statement? Remember? What was that? Yeah, exactly, right. You need to negate the statement. So we want to negate that, add it onto our list of clauses, and then do resolution from there. Okay. So I'll give you a few minutes to do that, and then we'll come back. Maybe just focus on the first one. Well, what does it mean to be unique? That's kind of part of the question, right? So we need to translate this statement. So what does it mean to be unique? So I've given you a hint before in this picture, right? So what does it mean to be unique? Maybe let's just talk about that first. So what does it mean to be unique? Right. So let's do the translation. So the least upper bound of set A is unique. So what does that mean? It means if I have two upper bounds, they must be equal, right? So what does that mean? Well, for all x and for all y, if x is a least upper bound, so s of x and s of y, then e of xy, right? We happy with that? I see a few nods. Yeah. So if x and y are both least upper bounds, then they must be equal. Okay. So that's a bit of a yeah. So those are the clauses that you would end up getting once you did the negation and turn it into clausal form. Okay. Maybe I'll just go back to show you the other clauses that you need.
Sorry.
Okay, so maybe I'll also give you a little bit more of a hint for this question. So when we have so many clauses, it can become a little bit confusing as to what resolution steps we actually need to do. So it's really helpful to think about how you would go about showing this normally, maybe without all this kind of additional logic notation. So how would we think about a proof by contradiction normally, right? Well, the first thing that we'd do is we'd imagine that we have two distinct least upper bounds. So we'd imagine that we have some sort of b and b prime, but we're imagining that they're not equal, right? So what do we know? Well, we know that they're least upper bounds, so they both must be upper bounds, right? So this goes back to the logic that I was talking about before. So b is an upper bound, and b prime is the least upper bound, so b prime must be less than or equal to b, right? And we can say the same for b prime. B prime is an upper bound, b is the least upper bound, so b is less than or equal to b prime. So what does that tell us? It tells us that B equals B prime, right? So that was that kind of intuition that we had. And so now what we need to do is we need to try to translate that intuition into the resolution proof that we actually do. So maybe I'll go through this example now. So here are all the clauses that we have, right? So this is after we negate that conclusion, we turn it into clausal form, right? We end up with all of these 11 clauses. So the first thing that I want to do is I want to show that B is an upper bound, right? Because that was the first step of my proof by contradiction. So what clauses would I resolve if I want to show that B is an upper bound? Do you have any ideas? Well, what do I know about B, right? I know that B, I know S of B. So what clause can I resolve with S of B that will give me something? Yeah, exactly, 4 and 9, right? So we resolve 4 and 9 under that substitution V goes to B, and we arrive at U of B. So B is an upper bound. It's exactly what we expected. Okay, so now if we follow the intuition again, what did we want to say? Right? We wanted to say that B prime was less than or equal to B, or B was less than or equal to B prime. Okay? So I want to construct some sort of sequence of resolution steps that gets me to something that makes sense. So what I might do is I'll say, okay, well, I know that B is an upper bound. So if I take anything that's like a least upper bound, it's going to be less than or equal to that thing. So the first step in doing this is I'm going to resolve this number 5 against number 12 that I just found. And then I'm going to use, right, the fact that B prime is the least upper bound. So how does that work? I just resolve number 10 against number 13. Okay. So this is kind of following that first, or if I go back to the intuitive proof, that's that second step, right? So we're saying B is an upper bound, right? B prime is the least upper bound. So therefore, B prime is less than or equal to B. Right? That's just the second step. Okay. So what would be the next thing that we do? So we've shown step 2. How would we do this for step 3? So that's kind of what we're thinking about next. So step 3 is B prime is an upper bound, therefore B is less than or equal to B prime. Well, we kind of do the same thing again, right? So we had these kind of 3 steps. We do a similar thing again. So we use number 4 and this time number 10 to show that B prime is an upper bound, right? And then we use the same clauses again to show that B is less than or equal to B prime. So that's the step 3 of our kind of English proof here, right? See some nodding? Great. So now what do I do? So now there's something that I can do that's really nice. I know that B prime is less than or equal to B. I know that B is less than or equal to B prime. What does that give me? Just
logically it makes sense that they must be.
yeah, exactly. They must be equal. So now I need to find some way to use my resolution to show that they're equal, right? And so which clauses came from that third statement? Well, it's these ones, right? 6, 7, and 8. So we already hone in on those to say, how can I use statements 6, 7, and 8 to show that B and B prime are equal? And the only one that makes sense to use is 6, right? Because I have 2 L statements, and this has like a not L. So that's exactly what I do next, right? So I resolve 6 against 14, right? And then I use that number 18, resolve it against 17, and I get that they're equal. Okay. So that's exactly we go back. That's exactly step 4. And now what do I do? Now I've got that they're equal. What now?
You get bottom from 11 and 19.
Yeah, exactly, right? I get bottom from 11 and 19. Sorry, the formatting is a bit weird there. Okay, so I get bottom. So what does that mean? What does that mean?
Both are unsatisfiable.
Yeah, exactly. So all of these clauses are jointly unsatisfiable, right? So what does that mean? Well, it means that the least upper bound of A is unique because we imagine that it's not unique, and then we showed that that's impossible, right? So we just done a proof by contradiction. Great. Okay, I think I'm running out of time, so I might just go. We might just skip that second exercise. I'll show you the mapping again. So this is, we had our proof by contradiction. We just mapped those steps onto resolution to give us a bit of an idea of where to go with the resolution refutation proof. Okay. Yeah, so the next one would maybe just skip it. The next one's a bit shorter, not too difficult. So if you'd like to do this, I'm not sure if this will be made available to you. If you'd like to do it, you can try it after. But yeah, good luck for your exam. This was a bit of a more difficult example than I would expect that you see on the exam. I guess the reason that I wanted to cover something a bit more difficult is because that way, if you can do the more difficult example, you know you can do whatever they give you on the exam. So all the best for the exam. And yeah, I'll hand it over to the next presenter.
All right, thanks everyone. We'll just come around with some snacks and we're going to have some sodas and drinks up the front. Just feel free to take like a minute or two. You've been sitting down for a while. And while you're doing that, we'll get the chairs in place. Sorry, do you mind if we move?
Yes, that's fine. I'll just move it out of the way. I think I should leave the.
That was really helpful.
Oh, no worries.
Thank you.
That's funny. Free to continue eating and drinking, but yeah, I'm going to power through the slides just so we can get to the questions. I think the questions are quite interesting, and the questions can be used as revision themselves. Okay. If I do go a bit too quick through some of the slides, please slow me down. But we'll see how we go. Okay, so I'm going to be talking about regular languages and what models of computation we use to recognize regular languages. And these are the things we learned at the very start when we moved on to models that are automaton, right? We looked at DFAs and NFAs, okay, deterministic finite automaton and non-deterministic finite automaton. They are very similar, okay? You can see on the table, the only difference is just what's highlighted in red, the text that's in red, okay? Everything else is the same in terms of the initial states, right? With any finite automaton, you start somewhere, okay? You can have 0 or more accept states for either of these models, okay? The difference is when we come down to the transition function. For a DFA, it's deterministic, okay? So at every single stage of reading your input string, you know exactly where you're going, okay? This is very important to remember. It's only one computation that can be made. There's no parallel computations. If you're at state Qi and you take input A, you know you're going to Qj, okay? The transition function tells you exactly where you're going. For non-determinism, we can have 0 or more transitions, okay? You have a set of transitions, a set of states that you move to. So if you're at state Qi and you get input A, you can go to 0 or more new states. Okay, that's where the non-determinism comes in. In the next slide, we look a little bit at where the non-determinism comes in, right? So over here, this was that idea I was talking about where, let's say you're at state 1 and you get input A, you can move to 3 states, 3 new states. This is just one example, okay? We also have epsilon transitions, okay? An epsilon transition, the way you think of this is as soon as you arrive at a state, if there is an epsilon transition, you take that immediately and you exist in both of those states. The one that you initially landed in and the state that the epsilon transition takes you to, okay? One tip, you've probably heard this quite a lot, but it's very important because this is how I like to keep track of the live states of your NFA, is you just use your fingers and cover which states you're at. So for example, let's say, imagine there was another state before this that took you to state 1, and that was our only computation at the moment. We weren't in multiple states. After we land in 1, we immediately take the epsilon transition. You've got your finger on both 1 and 2, states 1 and 2. So you're existing at both of them. Both of them are now live. Then when you read a new input, you just check where they take you. Okay. Over here, there's no other transitions, but just imagine that if you see an A and you're at state 1, that takes you to state 3, for example. Same thing with 2, let's say it takes you to state 4. You now move both of your fingers to states 3 and 4. Just imagining that we're there. Okay. I'm going to talk about some of the closure properties of regular languages. Okay. The closure properties are quite important to remember because you're going to get questions where they say, prove this language is regular. All right. Now, when you see that question or when you see the language, you might not know how to prove it's regular immediately. Okay. But you might find that it's a union of 2 other languages which are easier to prove, or an intersection or a complement of another language. Okay. These are important to remember because if you can't prove that a certain language is regular, think about these closure properties. Think if you can modify that language into 2 new ones and take the union of those. Okay. I'll quickly go through the ideas behind the closures, why we know it's closed on the union. For example, if we have two regular languages, we'll have two DFAs that each recognize those languages. Okay. I probably shouldn't use recognize because that's in Turing machine, but it's fine. But it's the same thing. Anyway, you got two DFAs, okay, one for language A, one for language B. Okay, we can now construct an NFA using epsilon transitions where we have a new start state, and then we take these epsilon transitions to each of the DFAs, and then they compute in parallel. Okay, that's why the union of two regular languages is regular, because we can construct this NFA. Okay, for intersection, we can, this is a different style of construction, but it still also works for union, and I'll come back to that in a second. But for intersection, if you've got two regular languages, now we take the cross product of those DFAs. Okay, so we've got two DFAs, we take the cross product. Here's an example. This DFA recognizes the language W has an even number of A's. This one is W has 1 or 2 B's. Okay, we take the cross product, so we now have 8 states. Going up and down is the same thing as going left and right with this DFA. Going left to right is the same thing as going left to right for this DFA. Okay, and then for the final states, it's just the intersection. Okay, so for example, we know 1 is a final state for this DFA. 2 and 3 are final states over here. The pairs, which are labeling these states, represent the first DFA and the second DFA. That's what the first and second element represent. Okay, so we want to go to a state which is in state 1 for the first DFA and state 2 or state 3 for the for regular languages. Complement, this is also quite easy to follow, because if we have a DFA that recognizes a certain language, the way we recognize or accept the complement is we just flip the states. Okay, remember, a DFA, we know exactly what state we're going to end up in. Okay, so we're either going to accept a string or not accept the string. If we don't accept the string, that means it's part of the complement language. So to now accept it, we turn those non-accept states into accept states, and vice versa with the accept states. We don't want to accept those strings anymore because they're not in our complement. So we flip accept and non-accept states. Okay. Concatenation, we can use a similar construction with NFAs. Okay. We have two DFAs for two different languages. We now want to accept the concatenation of those two languages. So what we do is we construct this NFA where from the final states of our first DFA, we have epsilon transitions to the start state of the second DFA. Okay. Clean star, we use kind of a similar construction to this, but we want to be able to loop as much as possible. Okay. So we take, if we have a regular language, which we want to accept, and we have a DFA for that language. Okay. To now accept the clean star, one thing we have to consider first is that we accept epsilon. Okay, so sometimes in your DFA here, this might have been a final state, which means we do accept epsilon. But to get around the fact that it might not be an accept state, we have to force our own. So we create a new start state, which is an accept state. We always will accept epsilon then. Okay, that's all this is here for, to just accept epsilon. Then we have an epsilon transition to come to the first state, the actual start state of the DFA. Okay, and that is so we can start computing, to start reading the string. And what we now do is from the final states, we have epsilon transitions back to the start state. That way, if we want to repeat a new word from the language, which is the clean star, we can repeat computation from that start state of the DFA. Okay. Difference. So if we have A and B, which are regular languages, and we want to compute the difference, we can actually just use set theory to modify A set difference B to become A intersection with the complement of B. Okay. And we know intersection and complement are closed for regular languages. So set difference is also closed for regular languages. Okay. So that's a quick crash course on regular languages. We'll move on to falling sets. Okay. So before we move on to the next level of computation, we want to think about how we can prove that a language isn't regular. Okay, that's why we have Falling sets. And what's the idea behind Falling sets? So there's a lemma that we use, the memorylessness lemma. It's a mouthful. But the idea is if we have a DFA M and we have two strings, X and Y, okay? If there is another string Z, which is our suffix, such that M accepts exactly one of X, Z, and Y, Z. So we're extending these two strings, X and Y, with this suffix Z, and our DFA M now accepts one, but doesn't accept the other, then we know that they don't have the same resulting state, okay? Those two strings in particular need two different states, okay? This is the key idea for Falling sets. This is why we produce this infinite set, or you can think of it as a set of size k plus 1 with arbitrary k. But if you have this infinite set where every pair of strings in this set are distinguishable with this suffix, then you've proven that you need an infinite number of states, which isn't possible for DFAs. It's a finite computation system, okay? I've given a general routine for Falling set proofs, right? You've probably seen this a couple of times. You saw this in the assignment as well, where I know I said infinite set, but you can think of it as a set of size k plus 1, keeping k arbitrary. So you create your set of strings, and then in that set of strings, for every possible pair, you come up with a distinguishing suffix that puts one word in the language and one word outside of the language, okay? And what that tells us is we cannot construct a DFA to recognize the language using k plus 1 states because all k plus 1 strings are distinguishable. And because we kept k general, no DFA can recognize, no DFA can exist. All right. Let's move on to context-free languages, okay? This is the next level of computation up. I've also got the table here for DFAs, NFAs, and now PDAs, push-down automaton. Okay, what's the difference now? I've highlighted it in red as well. We have a stack, so we have a stack alphabet, and the transition function is a little bit different because we now have to consider what's on the stack. Okay, that will tell us what states we can move to. So now this is what our PDAs usually look like. This is an example of one. This is an example of the notation for the transitions. This is how you can think of it, right? You've got your stack and your input, okay? And depending on what you receive in the input and what's on top of the stack, that tells you where to move. What else do I have here? The addition of the stack. Okay, yeah, so this is a classic context-free language, A to the N, B to the N, okay? Because DFAs and NFAs don't have memory, right? We can't recognize, we can't accept this language with a DFA. It's not regular. So stacks help with that because you can just push A's onto your stack as you read them. And then once you start reading B's, you pop them off the stack. If at any moment you see an A where it's not supposed to be, you terminate. But if you do end up seeing N B's, so you pop all of them off the stack, you end up accepting, which is exactly what's going on with this PDA over here. Okay. So yeah, let's talk about this PDA just a little bit. What do the transitions mean? Okay. One thing I like to think about is I like to put parentheses around these. The standard notation isn't to, but the reason why I put parentheses around these two symbols in my mind is because that tells me this has to happen before I can do this. Okay. What I mean by this has to happen is we have to read an input and we have to see something on the stack and pop it before we can push something onto the stack and continue with this transition. Okay. So this is saying you don't have to read anything. It's epsilon. Okay. You don't have to pop anything from the stack either. In fact, just push the $ onto the stack and take the transition. Okay. Over here, what this is saying is we have to read A as an input. We don't have to pop anything from the stack, but then we're going to push A onto the stack. Okay. So what this is doing is it's reading A's and pushing them onto the stack and staying at this state. Okay. Over here, for example, I'll do one more. Now we actually have to pop something. Okay. We read B from the input. As soon as we read B from the input, A has to be at the top of the stack. We pop it, don't push anything onto the stack and take this transition. Okay. And then the rest are very similar. But we'll move on. This is just the formal definition of how you should read the transition function. Okay, there's 3 inputs. It's what state you're currently at, what the input symbol is that you're reading in your string, what the stack symbol is at the top of the stack, and then new symbol for sorry, that's new state, not new symbol. So new state, there's new state you move to. Okay, and then a stack symbol for what you push onto the stack. But yeah, push onto the stack. Okay. Yeah, this is just an example. I think there's a couple more. Okay. Yeah, this is just the formal definition of what we have up here. That's also what we discussed. We'll also talk about context-free grammars, okay? Because these are also pretty good for proving languages are context-free, okay? We're going to talk about closures as well in the next slide. And closures with context-free grammars, at least for me, make the most sense. But if you want to construct a PDA to prove a language is context-free, that's also fine. But most of the proofs we'll go through use the CFGs. Now, a context-free grammar is a four-tuple. This is a formal definition. You've got your set of variables. You've got your set of terminals. You have your set of rules, okay? And you know what your start variable is. I think I've got an example on the next slide. Yeah, so there's an example here. So this is our start variable S, and it's got certain rules. One rule, for example, is to put an A and B at the front and the back and keep S in the middle, okay? And to keep doing this. And so what that rule does is it just places an A in the front, B in the back, okay? You can also have a rule like this, SS, which just concatenates itself, okay? Or you can just terminate, which is what epsilon is doing. Okay, this is another grammar which is a bit more confusing, but this does some mathematical expressions. Okay, and we've got some strange terminals. We only have A plus multiply and then parentheses. Okay, but this gives you mathematical expressions where A is the only number that you can. So you can have stuff like A plus A multiplied by A, put parentheses around that, and so on. Okay, and these are the rules. They also follow a similar style to this, but now the rules and our variables aren't like a single letter, okay? But the reason why I put this up is just because context-free grammars are used for parsing and things like that, and you'll see this in other courses, okay? Some useful summaries. These are things that we should remember, but when we want to prove languages are context-free, okay? CFLs are those that are recognized by non-deterministic PDAs, push-down automatons. Okay, so if you're asked to prove a language is context-free and you can construct a PDA, you've proven it's context-free. Okay, the other model, the generative model, the first one was a machine model, is CFLs are those that are generated by context-free grammars. So again, if you're asked to prove a language is context-free and you can construct the grammar, you've proven it's context-free. Okay, sometimes arguing about them can be a bit tricky. Okay, but sometimes if the language is relatively easy, such as A to the N, B to the N, that language or that grammar is easy to build and also argue about why that generates the language. Okay. Some closure properties of CFLs. Okay, so we got union. I said before that I'm going to talk about the context-free grammars. If you want to construct the PDAs, that's fine. Okay, but so if we have two languages which are context-free, we also have context-free grammars G1 and G2 for those languages. Okay, so then except the union, we construct our new context-free grammar G, which just has a new rule where we move to the start variable of each of those grammars. Okay, I just realized as well this should be a vertical bar, so we can go to either one of those. Okay. Concatenation is similar. We have two context-free grammars, okay? We now introduce a new rule as well. We construct a new grammar G, which has a new start rule. I've also called it G, which is a bit annoying, but this is a variable, okay? And this rule takes you to the start state for the start variable for G1 and G2, and you concatenate them together, okay? For clean star, it's a little bit different. So if we have context-free grammar for a language A, we've called it G1. Okay, we construct a new context-free grammar G. It's got the same rules as G1, but we now have a new start variable S prime. But what we can do is we can concatenate it with itself. So we can always introduce a new S prime if we want to start a new word. Okay, and then we also concatenate it with the start variable from our original grammar. Okay, and then we also have the option to terminate if we want to. That just means at the very start we can terminate. Or as soon as we've concatenated, let's say 3 different SG1s, we can terminate that. Okay. Finally, reversal. This one's kind of interesting. If we have a context-free grammar, which accepts a context-free language, we construct a new CFG, G prime, by taking the old one and literally just reversing all of the rules. Okay. This one might be interesting just to leave as like homework to play with and take your favorite context-free language, let's say A to the N, B to the N, take a context-free grammar for that, reverse all its rules and see how it generates B to the N, A to the N. Okay. Okay, we'll move on to questions. I might come back to the whiteboard so we can do some writing. Okay. Okay. I think the microphones have to change though.
Yep, audio should be working. Just checking 1 2 3 1 2 3. I think it should be working. Yeah, it's a little bit low, but yeah, it should be fine. Hmm? Oh, oh, yeah. Okay. Let's see. Check the. How'd you like it? That might work, yeah. Oh, right, yeah. Okay, cool.
Cool. Alrighty. So, the questions have been taken down, but I'll write up here.
Actually, could also screenshot. I know it's a background,
Yeah. Okay. So I've written up the both languages that we had on the screen earlier. Okay. And the first question said prove or disprove that these two are equal. And then it's implied that we're looking at for all languages L. Okay. So if you ever get a question that's prove or disprove, in particularly if you think you're trying to disprove it, so you have a feeling that they're not actually equal, okay, think of examples straight away. That's the first thing you have to do. Come up with examples and see what happens. Play around with both of these languages, see what they do, okay? The first thing I do, let me just make this clearer. So do of L stands for double, SQ of L stands for square, not the database languages or database language. So when we double, we can double any two strings in our language. So if we have W and X, which are both in L, for any words, any two words W and X, we can concatenate them together, okay? For SQ of L, we have to concatenate the same word together, okay? So immediately that should start throwing you off and making you believe that we have to disprove these are the same. And also when you come up with your examples, keep it simple. Just see what happens when you come up with small languages, because if you want to think about really large languages, it starts to get a bit tricky. But what I'm going to do is I'm going to take the language L equals 0, 1, okay, and see what happens for both of these, okay? Let's actually start filling out double of L, okay? Again, we can concatenate any two words in this language, but for every single possible pair, okay? This is just the set 0, 0, where I concatenate 0 with itself, because that's possible, okay? I can also concatenate 0 with 1. I can concatenate 1 with 0, and then finally 1 with 1. Hopefully you can see straight away that if I take square of L, because I have to concatenate the same characters together, or the same words, sorry, I can only end up with 0, 0 and 1, 1. Okay, so we've come up with an example where they're not actually the same. So we've disproven that they're equal, so we can just say, therefore, do of L does not equal square of L. Okay? Oops. Okay. The next question was, if L is regular, is do of L regular? Okay. So what is do of L actually doing? What's the definition up here? Is there another way we can rewrite it? Well, I've given a bit of a hint to what it is by saying the word concatenation, right? We're actually concatenating words W and X from the language L for every possible word, okay? So in other words, what do of L is it's just the language L concatenated with itself. Okay? So now we know from this line, if L is regular, I'm using a closure property here. If L is regular, then the concatenation of L with itself is also regular. Okay? Therefore, do of L is also regular. Because do of L is equal to L concatenated with L. Okay? That's question 2. I'll just do the last one. So the last one is a bit wordy, but essentially it's just asking, because we've proven that do of L and square of L aren't the same language, and we know do of L is regular, are they both regular? Or in other words, is square of L not regular? And so now we're going to use a fooling set proof. Okay? So this is question 1, 2, 3. Okay? And so again, we have to take some language, okay, so that we can use square of L, and we want to keep it simple. Okay? This doesn't look so simple when I write it like this. Okay? But really, this is just every possible string. Okay? So that is kind of simple because it's the universe, and the universe can be easy to think about at times. Okay? And so what will square of L be? It's actually just a set WW, where W is in this. W can be any string we want. Okay? Alright, so now what I want to think about is I want to think about coming up with some strings which are distinguishable in this set. Okay? And so the set that I came up with for the fooling set is 0 to the I1, where 1 I k plus 1. Okay, so this is the first step. Okay, when you write this in an exam, try to make it a bit more formal. I'm kind of going to skip over a few things here just to keep it brief. But this is a fooling set of size k plus 1. Okay, and I've come up with these strings 0 to the I1. Okay, why is this a good string to use? Or why didn't I just keep it as zeros? Well, if you kept it as just zeros, right, then any string that is an even number of zeros will be in the language. So adding a suffix to just a word of zeros will be a bit tricky, okay? Because when you double it, it's going to be an even length string, okay? So working with just zeros is a bit tricky. When you add a 1 on the end, what that does, it adds an endpoint for the word you're working with, okay? So now let's think about 2 different words in this language, okay? I'm going to take 0 to the I1. So this will be word I, wj equals 0 to the j1, and I does not equal j. Okay, so now what I want to think about, so I've got 2 different words in this fooling set. Okay, I want to think about how I can distinguish these 2 words. Okay, well let's say I double 0 to the I1. That's my suffix. My suffix z is just 0 to the I1. Okay, that word is clearly in SQ of L. Okay. Now over here, 0 to the j, because I is not equal to j, right, I'm not actually doubling this word. And that's the importance of having this 1 here, right? Because the first bit is j zeros with a 1 on the end. The next bit is I zeros with a 1 on the end. And I and j aren't equal to what we've assumed over here. We've taken 2 different strings. So if I take the suffix z, which equals 0 to the I1, I'll continue up here just so we can all see. What you end up with is wiz equals 0 to the I1, 0 to the I1, which is in square L. Okay, wjz is equal to 0 to the j1, 0 to the I1. This is not in SQL. Okay, we've come up with a distinguishing suffix for every pair of strings in our language. Okay. Therefore, square L can't be regular. Okay, I'm going to, actually it's showing working on the board there. There is another question, okay, which talks about context-free languages. I won't cover that just in the interest of time because Colson has to speak. But there is a bonus question, okay, that I've added because the exam question I saw was, The fourth question was, prove that this language is not context-free, okay? We actually don't have a way of proving a language isn't context-free because we don't learn the pumping lemma in this course. That's what you use to disprove a language is context-free. But it is still a good idea to think about how you would approach that problem without this lemma that we would use, right? Because I think if you can understand what makes a language context-free, or if you can, understand what makes a language not context-free, it'll help you understand why languages are context-free. At least get the intuition for it. So yeah, I'll leave those as homework for you guys to look through. But yeah, I'll move it on to Carlton. Okay. But so you haven't answered them. You can put it back on the presentation. It's on Zoom. Oh, actually, okay. Oh, no, there. Sorry. All right. Sorry, everyone, that we're running a bit over time, but let's talk about our favorite part of the subject, obviously, the section on streaming. Okay, so we've just talked about our different machine definitions for recognizers for regular languages and also context-free languages. And we're moving up a level now by going to the Turing machine. So the way that we're conceptualizing this as a machine is a Turing machine that involves using a tape, right? So we've defined it that way. There are lots of equivalent models of computation that have the same expressive power as a Turing machine, but Turing machines are kind of cool. We have this like visceral understanding of what a tape looks like, you know, from old school computers. So we've kind of stuck with that rather than something like landing calculus, which is a little bit more abstract. Okay, so our attempt to increase the power of these recognizers is by adding this new form of memory, which is more flexible than what we've seen with a PDA, right? PDAs had one cool extra feature that were added to them, which was what? The stack, right? And the stack had one especially cool thing about it. It was what? Yeah, it has infinite memory, which is pretty awesome. But it was limited in terms of how you could use it, right? So it could remember as much as you could throw at it, but you can only access the head, right? So you can only pop off what's at the top. You can't randomly access parts of that stack memory, right? So a Turing machine is actually equivalent to what we're used to with a traditional computer that you're used to every day. You can actually treat it effectively like random access memory, even though you do have to scan through this tape, which is kind of annoying. Technically, because you can mark things in arbitrary ways, you can sort of zoom along the tape and treat it as if it was random access memory, right? So by the time that we've added this tape construct, now we're at a fully functional computer that can do anything that we are used to with our kind of algorithms. Like, you know, we've sort of come like full circle at this point. We've been very abstract for the past 12 weeks, or the past 10 weeks, I guess, when we started talking about this. And now we've come back to, you know, your laptop that you were using since the first semester of first year. Okay, so this is a sort of diagrammatic form of a Turing machine. I'm not really going to talk about this too much. Similar to what we've seen for other machines, but now, you know, we have the ability to move left and right in our tape. So the post condition that we have includes what you're putting on the tape, but also how you're moving the tape head after you make that fit. Okay, so yeah, this is the machine that we saw from tutorials that is doubling the number of ones on the tape. So it's interesting and important to remember that Turing machines can be more than just recognizers and deciders. We kind of focus on that as we go later along. But sometimes we care about what's actually left on the tape when the Turing machine is done, right? Because at the end of the day, we're treating these like they are models of computation that can compute anything. And the only way that they return values is by just leaving something on the tape. You can read what was left. So the question that we are interested in now is something going to halt? I don't know if anyone remembers the wheel of blend, but that immediately came to mind when I was making this slide, so it's up there. So we didn't have this problem up until now, and it's kind of interesting to think about why we haven't had this problem up until now. We haven't had this problem with our previous machine models because they all finished.
right? Because they only had a certain number of characters that they were actually consuming. And after you consume them, then you're done. You didn't even kind of halt the machine in a way. It's sort of like you just sort of executed a certain number of steps and then you tested, like you opened the box. You looked at what it was. Is it in an accept state or not? And then you just take that as your reading, right? It's not like the characters, the machine sort of had control and then returned control to you. Right? Turing machines, though, they don't have this hard limit, right? They don't have the same kind of value that is going to increment and make progress over time, right? We didn't really talk about that in this iteration of the subject, but there's no condition that you can place some sort of limit on such that every step the Turing machine makes, it is bounded in terms of it's going to reach zero eventually, okay? Which basically just means that you can write an infinite loop in your machine. They halt when they want to halt, right? Whenever they feel like it, then they'll say, yeah, I'm done, or yeah, and accept, or yeah, I'm done, and reject, right? Again, this is different to what we've seen in the subject, but it's very much the same in terms of what you've seen in everything prior to the subject. Right, so like I said, we're used to this, the machine has control of when it's finished. So what we get from changing this modality is that we can recognize more complex languages, we can perform more complex tasks, and the price we pay for that is non-termination, possibly. Okay, so that's sort of just a recap of what Turing machines even were. The Church-Turing thesis, anyone remember what that was? Yeah. Good.
Any reasonable model of computation expressed using.
Yep, exactly. What does reasonable mean?
Just any of the algorithms we use today when we
Yeah, good. So there might be some like hyper-computation model that we're not aware of yet. No one has proved that that doesn't exist. But I think for most cases, we're fine with just treating this as if it is fact, right? So any model of computation that could possibly exist can be executed or run or recognized, etc., using the Turing machine model that we are used to. Okay, so anything that we can do can be executed on a Turing machine if you give it enough time. It's not necessarily an efficient way of doing it, but it's capable. All right, so there isn't extra hardware that we can give to Turing machine to enable us to do additional things, right? Previously, when we're moving through these iterations, when we're going from DFAs, PDAs, up to Turing machines, we're sort of like changing the machine, we're upgrading it, putting more things in. And what we're saying is that there's no more things you can add to a Turing machine to somehow make it more competent. Okay, so yeah, we basically just showed this in lectures. I'm not going to go through and reconstruct these, but two machines that are interesting to sort of think about, again, because they're sort of, it's interesting that that doesn't make it more powerful, but also useful for proofs potentially, is the fact that a non-deterministic Turing machine is only as powerful as a deterministic Turing machine, and also that a Turing machine that has suddenly more than one tape bed is actually still only as powerful as a single Turing machine. In terms of thinking about these and sort of rationalizing that, the way that we did that was we added some control characters, which basically allowed one single-headed Turing machine to simulate as many Turing machines as it wanted, right? Again, that sounds really weird, but if you take a step back, has everyone here done computer systems or thought about parallelism at some point? Your computer that has a single core can run multiple programs at the same time. How does it do that? It just sort of iterates really quickly through one instruction of each of the programs at a time, or multiple instructions before handing control back, right? So we can do the same thing here by just saying, look, we've got this infinite tape. Let's just set up a whole bunch of Turing machine states. And then the main overall real Turing machine function is kind of going through those different states, taking one or two transitions and then moving on to the next one, doing one or two transitions on each of them, right? So that's how we can run multiple Turing machines in parallel on one Turing machine. Okay, so I'm not going to really talk about that anymore because we don't have that much time. Get on to the interesting part, the decidability and recognizability of things. Okay, so we already discussed that if you give a Turing machine some input, it can do a couple different things. It can return back yes and accept. We're not really caring about what it leaves on the table at this point. We're just caring about what it says accept or reject wise. It can reject, or it can just run forever, right? You get a control C at some point. So that leads to these new language classes that we've thought about, right? So first we'll talk about decidable. So imagine there's some language L. So actually try and imagine a language. It doesn't have to be anything complicated. It can just be a set with the strings A and B in it. Right? And then we've got some Turing machine M. If it is the case that when you give the machine M some string from L, it always says yes. And if you give that same machine some string that's not an L, it will always say no. Then what you've got is a decider. Okay, that's as simple as what it is, right? The decider is just a Turing machine, which is returning yes or no for set membership to say, yes, this string is in this set or not, right? And this is a nice thing to have because it's always going to tell you yes or no. It's never going to get stuck thinking about it. So conversely, or not conversely, but I guess an alternative is that we've only got what's called a recognizer. A recognizer is a machine which will always say yes if you've given it a string that's in that set. But if you give it a string that's not in that set, it might think about it forever. Okay, it might just sort of guess and check, guess and check, guess and check, guess and check, generate a new option, check, generate a new option, check, generate a new option, check, for all of time. Okay, never actually finishes. In that case, M is what we call a recognizer. Right? Now, there are things outside of the Turing recognizable languages. We might talk about that at the end if we get some time. But yeah, for now, we're talking about those two language classes. So this is a table here because I find that people often get confused between the idea of a decidable language and a decider, right? So there are two different things we're talking about here. We're talking about Turing machines and we're talking about languages still. We've been talking about languages for the past 6 weeks and they're just sets of strings, right? But we've introduced the fact that, hey, there are different types of Turing machines have different ability to say something about these languages. Either say yes or no, for sure, it's the decider. Or they might only be able to say yes for sure and sometimes say no if they, in certain circumstances, okay? So the relationship between this is that we say, if you've got a decidable language, that's a language which it is possible to build some Turing machine that acts as a decider, okay? So if you see the term decidable language, what that means is that there exists a Turing machine which has those properties we just said before. As in you can build an algorithm to say, yes, the string is in that set, or no, it's not, right? Conversely, a recognizable language is one that is a language where it's possible to build a recognizer for it, okay? So we'll think about that in a second. So now it's time for your pop quiz. So not to the front of the class, but in the people in your group around you, talk with the person next to you. Try and answer these 5 questions. And we'll come back together and discuss them for maybe in 3 or 4 minutes. Who wants to have a go at answering some of these? So question one, anyone got any ideas? Yeah.
It is possible to have a decidable.
Yes, exactly. So if you know that there's a decidable language, that there exists a Turing machine which acts as a decider, right? And what was a decider? That's question two. The behaviors of a decider. Yeah.
It recognizes the language it wants to read.
Yeah, so more specifically, so it's going to halt in every input and it's going to say, yeah, yes or no to that. Exactly, yeah. I get what you mean, but maybe using the word recognizing is a little bit too better. It's good. Okay, so it's going to halt and say yes if the string you gave it was a member of that language, and it's going to halt and say no if it wasn't a member of that language. Eventually, right? We're not saying that this is going to happen in any kind of reasonable time frame. It might take until the heat death of the universe to say yes or no, but eventually it'll get there. All right, what about a recognizer? Yeah,
It could run.
yes, okay, so that's half of it, but there's a really important condition.
Oh, it still exists.
Exactly. So it can only run forever if the string you gave it is not part of its language. Okay, that's a really important distinction to make. Yeah.
What quality of a language makes it recognizable?
Recognizable but not decidable. Okay, so for something to be Turing machine recognizable, it needs to be what's called recursively enumerable, which means that you can list everything out and eventually generate every element of the set. And that's actually going to come into play for the next questions 4 and 5. So we'll get back to that as a good question. Okay, so question 3, is that set recognizable or decidable? It's decidable, yeah. So how would you, so okay, you claim it's decidable. What do you need to do to prove that?
I can make a DFA.
Yeah, great. And you can emulate a DFA on a Turing machine. Perfect. Okay. What about recognizable then?
All decidable, I recognize.
Yeah. So if you can build a decider, then it's definitely recognizable. Excellent. Okay. Right. Because we're just saying a recognizer has the opportunity to run forever if it really feels like it, right? But it doesn't have to. Okay. Questions 4 and 5 are sort of related. So the game is that I'm thinking of a real number, and all I'm going to say is yes or no when you guess what it is. Okay. Do you think you'll ever be able to get it, or are you sure you'll ever be able to get it? No. Why not?
You could go on for infinity.
Yeah. We've gone for infinity. Yeah. But aren't there? So question 5 then, there are also infinitely many natural numbers. Right. But hopefully we sort of understand that if we're playing with the natural numbers, eventually you're going to be able to win, yeah, if you're just guessing.
I think we die before then.
Possibly, yes. But imagine that we're some sort of beings that can live forever. Eventually you're going to win the game. Or you're a machine who can execute billions of operations per second. So what's the difference between those two types? We've got different types of infinities here. Yeah?
Real numbers are.
Yes, so what does that mean? Exactly. You can't assign an index to each number, right? The natural, so what it actually means to be uncannily infinite is you can't map the natural numbers to some infinite set, right? You can obviously map the natural numbers to itself. It's pretty easy, pretty trivial. But what that means in practice is that, like I said before, we were talking about the question regarding part 2, is that you can enumerate all of the natural numbers, okay? So if we're playing this game, what is going to happen is that if we're working with the natural numbers, I have to commit to a natural number. It's kind of analogous in a way to what we're talking about with like the DFA proofs when we're talking about the set. I have to commit. Actually, you know, I'm going to build a DFA with k states, or I'm going to choose a natural number x. At that point, I'm locked in with that natural number x. So you can just guess everything from 0 and eventually get up to x. And eventually you'll get there, right? Eventually you will guess my number. So hopefully it makes sense that this kind of problem is what we call recursively enumerable, be guessing the natural numbers, okay? Which is why you can build a recognizer for things that you can enumerate through. However, for the real number problem, even if we just restrict the domain of the real numbers to just the game between 0 and 1, you're still not ever sure if you're going to be able to guess my number, right? Because you can always just keep halving, right? You can go between 0 and 1, you can guess 0.5, and then you can guess 0.25 and 0.125. So you can always get into these smaller and smaller gaps that you can never be sure that you're going to exactly guess my number. Because I could just guess some real number with effectively infinite digits after it, right? Some irrational number that you can never actually guess effectively. And you'll never be able to enumerate to it. Okay? Does that sort of make sense? Yeah.
So what is the connection exactly between something countable or uncountable Turing machine?
Okay, that's a good question. So I used the words recursively enumerable before. The Turing machine you can make a Turing machine conceptually, which is a recognizer for something. So remember what a recognizer means. It's a Turing machine that if you give it something, it will eventually say yes. So we can build a Turing machine, which is a recognizer for checking if something is part of the natural numbers by just having the Turing machine go, okay, what I'm going to do is just generate 1 and then check if what I just generated is equal to what you gave me that string, right? Is 1 equal to 1? Yes. Easy, returns yes. If you guess, 1,367,302, then eventually the machine's just going to go, okay, I'm going to generate 1. Is that equal? No. Generate 2. Is that equal? No. And it'll take its time. It'll eventually get up to 1 billion, whatever I said. And then it will check, is that thing that I just made equal to what you said? Oh, it is. Done. Finished. Right? Return true. It is. If you give it something which is not part of the natural numbers, like A, it's going to use that algorithm and just never ever match on it. Okay? So it's a recognizer in that if you give it something which is a member of the set, it can generate all the members of the set, and eventually it will generate that thing that you were asking it to check. Okay? But if you give it something which is not a member of that set, it's never able to generate it. And so it's never able to say with certainty, oh, okay, the thing you gave me is not in the set. Because it's just going to keep guessing and checking until the end of time. Right? So if it can't enumerate everything and then guess and check in that method, then it is not decidable. Okay? So it might be recognizable. This problem is recognizable, but it's not decidable. It can't for certain say, oh, you gave me an A. Like that's not in the natural numbers. Okay. Does that make sense? Hopefully. Yeah. It's recognizable, yes. Then it's not in recognizable.
So then it's definitely not recognizable.
Definitely not recognizable.
Okay.
Yeah. Yeah.
What about the rational numbers?
What about rational numbers?
Are they recognizable?
Well, that's an interesting question. What do you think?
No.
Why? So an easy way to
Not countable.
Yeah, they're not countable. So kind of the easiest way to think about why they're not countable is because for any fixed denominator, you could choose infinitely many numerators. And for any fixed numerator, you can choose infinitely many denominators. And that's a new rational number at that point.
They were countable though.
Are they countable?
Yeah.
Someone Google it. Yeah.
When we say irrational numbers,
So we're good.
we say irrational numbers are countable.
No, the irrational numbers are not going to be countable.
Why is a fixed number?
But that's what I'm saying. So you could enumerate pi to all of infinity, right? So there's no way to kind of enumerate pi, or all the irrational numbers. What? They are countable. Okay, then you can recognize them. Yeah. So if you can count all of them, then you can eventually, I guess.
But you can't use the argument that if you restrict the between 0 and 1, there's sort of equally many rational numbers, but there's sort of quantum. So
yes, but if you can count them, that just means that you can eventually. Yeah. So I guess it's not because it's between 0 and 1, because like if I said you fix the denominator, you change the numerator, eventually that's gonna sort of get it up. Like, there's only a certain width or ratio between the denominator and the numerator such that they stay within some intervals. I'd have to think about more of that. Yeah, if you could say that they are countable, then you can enumerate. It's fine. You can cover the other. All right. So last thing, sorry, we're running over time, is the decidability problems and reduction proofs. So we have talked about these few problems for all of the language classes that we've seen up until now. Okay, acceptance, emptiness, and equivalence. So we should memorize the decidability properties of these different problems for each of the language classes because we'll be able to use those as proofs for later. So this is unfortunately something you kind of got to learn, but some of them sort of make sense, at least for the regular languages, at least. Right. So for the regular languages, the acceptance problem is decidable. Hopefully we're all happy with that because like we said before, you could just build the DFA, run the DFA, it's definitely going to finish, right? And we know that we can simulate DFA using Turing. The emptiness problem is also decidable because, well, the easiest way to think about this is sort of like a graph exploration algorithm on your DFA. So you think about, okay, I'm going to start the start state, I'm going to kind of work my way around. If I ever find an accept state, then that means there's some combination of steps that would get me to an accept state, right? So it must have some string that it accepts, it's not empty, okay? And then the last one is the equivalence problem, which is checking are two DFAs equivalent and that they have the same language that they recognize. That is a decidable property because we can do, like Mark was saying before, we can actually compute DFAs for things based on the intersection and the complement. We can set up this new DFA, we can generate a new DFA that does this, and we just use the emptiness check that we said before to check if this new DFA is empty. So if that's empty, then the two are equivalent. All right, so we've got to just sort of remember those three. Context free, the first two are again decidable. We don't really talk about normal forms here. So you just kind of remember, but the normal form, Chomsky normal form is basically rewriting things in a way that rules can only expand into two different things. They can never have more than two variables of terms, okay? So then we can just expand, make sure we've generated all the strings of a particular length, and then just check again, sort of if any of those are equal to the string together. Emptiness, you can prove via CFGs, right? Basically just work backwards and make sure that you can actually reach the starting symbol from any terminal. So if you can, by sort of chaining backwards, then at some point the CFG can make a string that has a character in it. Equivalence is undecidable. So we've reached our first undecidable property. And there's no representation of a context-free language in which you can actually prove that they are equivalent to each other, decidedly. Okay. So didn't really talk about the proof of that, but it's just useful to remember that because we'll use them for our proofs later. Yeah.
For acceptance, what do we have to see?
For in a context-free grammar. Yeah. So the context-free grammar, you can't really think about it as sort of never terminate, or you mean just like a context-free grammar that doesn't actually have an ability to terminate at all? Yeah. Then okay, that's called like non-productive, I think is the term for it. It doesn't actually ever produce anything. And at that point, it's just considered to be empty. It doesn't actually have any output. Because you can't ever, it's sort of like you think about all of the strings that it could generate and that can't generate anything. So there's no path to ever put out a terminal. Very good. Okay. Good question though. Okay, and then the last bit here is we've talked about some different decidabilities of problems for Turing machines, right? And we've shown at various points that these are undecidable. We've got a proof that, in a second for the emptiness problem being undecidable, but we showed via sort of the halting problem that the acceptance problem is undecidable, and also the equivalence of two Turing machines is undecidable, which sort of makes sense. If you can't even check if somebody's going to accept a string, then it sort of makes sense that you can't check if two things are equivalent to each other. Okay, so the first one is something that we proved via the halting problem, which is Alan Turing's famous proof. I'm not going to run through this because we're sort of short on time, but basically this was just a logical argument to show that it's not possible to build some machine H which checks that it on a given input a Turing machine will halt or not in a decidable manner. Okay, so that would be really nice to do, because if you could build this halting machine H, we would never have to worry about recognizers, because anytime that we're like a little bit scared that maybe this Turing machine is going to run forever, we'll just firstly use the halting machine and check like, hey, halting machine, is this machine ever going to run forever? And if the halting machine says, yeah, it's actually never going to stop, it's going to run forever, then we just won't run the machine and we'll just return false for that. So we could build a decider at any point using a recognizer if we had a halting machine. Anyway, so you could go back and sort of revise this. The proof itself is not, I think, directly accessible, but the outcome that the halting problem and the basically equivalent acceptance problem, they are undecidable for Turing machines. Okay, so we need to remember those properties because we need to use them for reduction proofs. Okay, so what is reduction and reduction proofs? It's basically a proof structure that lets us reason about existing decidability classes of problems that we've encountered before and extend that to new decision problems. Okay, so we do effectively something that looks like this. We kind of have a subroutine, right? We can think about these as functions that is solving some problem that we know is decidable or undecidable in a certain way. And we use that to build an outer machine, right? Potentially with some sort of little transform called the reducer inside of there as well, just to change the format of the input for the outer machine H into the input required for the inner machine R. So let's do an example together. We are going to show that the emptiness problem is undecidable, okay? Using reduction of the acceptance problem to the emptiness problem. So what do we remember about the acceptance problem for Turing machines? Is it decidable?
No.
No. Okay, so that's just a fact we need to know. Kind of rationalize it, you kind of think about it, but at the end of the day, it's fine to just say, from lectures, I remember that you said the acceptance problem is undecidable. Done. Okay? So, the acceptance machine, what it's supposed to do is it takes input of a form. When you see these angle brackets, by the way, that just means like a string encoding of a Turing machine. So it's a way to take a Turing machine and give it to another Turing machine. So we've got the Turing machine N and the string W. And the machine ATM is going to accept exactly if W is in the language of that machine, else it will reject, right? So this is a decider, right? We're saying that this is decidable. Sorry, it's not decider, but if it existed, this is what it would do, okay? That's a machine that we've thought about, and we said, no, you can't do that. So the emptiness machine is one that is supposed to take a Turing machine and return yes, if that machine has no strings that are recognized, and so it never says yes to anything. A little bit confusing, but so if the language of the machine is the empty set, then the empty machine is going to say, yep, that thing's empty. There's nothing in there. So with that in mind, let's build a new machine in an interesting way. So what are we asking the question about is this, right? What we know is that this is undecidable, right? We're trying to figure out, is this decidable? Using the fact that we know that this is not decidable. So what we do is we build this, this mythical machine, which uses the emptiness decider, right, to build an acceptance decider. Now, we proceed by proof by contradiction. So we've seen this quite a few times in the subject. We're coming back to it again. So the proof by contradiction always works in a particular way, right? We make some assumption, we reach some logical inconsistency, and because we've reached a logical inconsistency and we only made one assumption, we can conclude the assumption we made was wrong, right? That's how it always proceeds in any kind of proof of contradiction. So here, again, the goal is to show that the emptiness problem is undecidable. So the approach is that we're trying to build the mythical acceptance decider, which shouldn't exist, using the emptiness decider. So the assumption we make, the one assumption, is that we assume that there is a decider for the emptiness problem, as in ETM exists, right? So using that machine that we assume exists, we're going to make a new machine which functions as an acceptance decider. And as part of that, we're going to create a reducer, right? The reducer is going to create a new Turing machine M prime, sorry, which has this language. So the language of the new Turing machine that the reducer makes is the intersection of the string W and the language of the original machine that we give to the outer machine. Okay, so if we can create that machine, then we know that the emptiness machine does not exist. It does not exist, right? At least as a decider, because we've managed to create something that shouldn't exist, right? We know that this thing, the acceptance decider, is mythical. It's not real. Okay. So if we made it, then something is wrong. That's our logical contradiction. We know it shouldn't exist, but we just made it. Therefore, the one assumption we made, that this exists, is incorrect. So the trickiest thing about doing this is coming up with our reducer. So we're going to want to take the input for this function, right? So the acceptance decider is one that takes a machine and a string, and it's supposed to do what? So your function as the acceptance decider, you get given a Turing machine and a string. What's your job to do?
Want to see if it accepts it.
Yeah, exactly. So your job as the acceptance machine is to say yes if W is in the language of that machine, or no if it's not. Happy with that? So the input of this function is a machine and a string, and the output is yes, it accepts that string, or no, it doesn't. Okay. So again, this is sort of like function composition, very used to this software engineering stuff. So you can just ignore this and pretend it's a black box, and that's what we're going for, right? So that's sort of the function definition is it should take in that structure and give it out like that. So to do that, we want a reducer, which is going to take in the same types, right? And change them to some format that we can give it to this other problem decider that we have, right? So the emptiness decider doesn't take a string, it just takes the Turing machine, right? But we can build a new Turing machine in our reducer by just throwing some strings together, right? I formatted this as like a higher order function, right? Because that's sort of more what we're used to. It's a function that returns another function, because Turing machines are just functions, right? Effectively, they're just algorithms. So this, the reducer, is a function that takes in a function and a string and gives out a new function. Yeah. So the reducer takes in a Turing machine string representation and a string. It returns back a new function, right? Which is just taking in this new function, just takes in a string, which is what this emptiness decider wants, right? It just wants one string. Okay. Okay. Oh, sorry, no, it doesn't just want one string. We're giving back just one machine, right? That's fine because the emptiness decider wants one thing. So what the new function is going to do, this new Turing machine M prime, what it does is it just checks if the string that it's been given is not equal to W. And if it's not equal to W, then you reject. Otherwise, it just returns the original machine and what it says about that string. Now, this is really confusing because where did X come from? What is X? Why are we checking if it's not equal to W? And the answer to that is to realize two things. Firstly, if I just go back, we're trying to make a new machine M prime such that it has this language. What is special about this language? What could this language look like? There are only two options that LM intersection the set of W could look like. What are the two sets it could be? Yeah,
It's W or it's M.
it's exactly. It's either the empty set or it's the set which is W in it. Convince yourselves that that's the case. Right? Doesn't matter what M is or the language of M is. All right, but it doesn't really matter. There's only two cases, right? And one of those cases is interesting. One of them is the empty set. Yeah. And if we've got an emptiness decider, I think it can say something about that, right? So it can choose, the emptiness decider is going to tell us which of those two categories we're in. We're either in the empty set case or not. Now, when does the empty set case happen? When is this the empty set versus when is it the set which is W in it? Exactly. Yeah. This is the empty set if M does not accept W. Right? So if W is not in here, then the intersection of that and that is the empty set. Right? If W is in here, then the intersection of this and this is W. Right? So what we could do is give this to the emptiness decider and have it say, oh, this is the empty set. Great. The only time it's the empty set is if the original machine actually accepted. Sorry, if it didn't accept that string. Right? It's not empty as in it has the string W in it if it did accept that. So It's an interesting thing because, and this sort of speaks to intuitively why it doesn't make sense. We're still kind of running the machine in this function, which is like, yeah, how is that possible? Like, what if this is not a decider itself? It could just run forever. So doesn't that mean that this is going to run forever? Does it? Thoughts? The answer is no. And it's because, like I said before, we're never actually executing this function. All we do is we execute the outer function, the reducer. We make this, and then we just give it to the emptiness decider. Right? So you should be sort of having some alarm bells go off. And how is the emptiness decider going to use that necessarily? If you've got a recognizer in there, it's not a decider. How could it be decidable? But we don't care about that, right? We just care about making the reducer function a decidable problem, in that it can generate this function, and it definitely finishes doing that. Okay, so it makes this, it ships it off to the emptiness decider, and then it returns back yes if it was empty. Oh, sorry, it flips the output of the emptiness decider. Okay, because this function, it exactly has that language we talked about before, right? It has exactly this language that the language of M prime is the intersection of the set W and Ln. The reason why it is, it's actually similar to, there was a tube question that was basically the same as this, in a way. The way that we test that is we basically just say, look, if the string you gave me is not W, obviously it's not in the intersection of W and whatever you give me, okay? So we're just going to reject that. We're just going to say no, okay? Because to be in the intersection of the set of just W and Lm, it has to obviously be in the set with just W in it, okay? So if it's not W, done. Otherwise, return whatever M said, right? That's what effectively the set intersection means. It needs to be in the one set, which was just the set with W in it, and it also needs to be in this set. Happy with that? So this is just an algorithm for finding, hey, is X in the intersection of the set with just W in it, which is what this checks, right? Is it in that part? And if it is, it also needs to be in the other one, because that's how intersection works. So you just say, okay, yeah, return whatever X said. We're going to execute that. We never actually run M prime. We just give it to the emptiness decider and then see whatever it has to say about that. Okay, so you can ruminate on that. It might take a little bit of thought to kind of fully sink in. But yeah, so notice that if that's the empty set, like we said, then it maps exactly one-to-one with saying that W was not in the language of the original machine. Yeah?
When we say that's an intersection can't in the previous slide,
yeah,
we need to take advantage of the closure properties sort of thing there, or?
No, you actually don't, because we're not saying anything about this, and that's why it's interesting, right? We're not, it's suspicious, right? Because we've made some new machine and it hasn't relied on any kind of property in terms of like, is this decidable or recognizable or anything? Who knows? It's just a random language of some Turing machine. Okay, so it's kind of a signal of the fact that we know this isn't going to work out. The emptiness decider is doing some weird hacks to be able to do this. And it turns out actually just means that we can't build an emptiness decider before. Okay. So basically, because we were able to build this machine, which does exactly what we said that a machine cannot do, which is act as an acceptance decider. Therefore, the one assumption we made, which was what? Yeah, that this even exists. That one assumption, wrong. Therefore, proof finished. There is no decider for the emptiness problem machines. Okay. Okay, so I've got an easier problem for you to work through. I know we're well over time, so feel free to head off if you've got it. But a kind of simpler problem is to show that the acceptance problem for Turing machines is undecidable by reducing the halting problem to the acceptance problem. So I mentioned a few times that was the case, but yeah, you can try doing that. Are we over time? You gotta go.
Okay, so feel free to work on that if you like, but I've got a few announcements and then, yeah, we can discuss it afterwards if you. Right. So thanks everyone. So don't worry about the empty time. Thanks so much for coming to the mock workshop today. We have an S&D workshop in about 30 minutes. If anyone here is doing that as well and also has the rest of the argument instead. But we just give another round of applause to Jonathan. They'll be available in this Discord, which is probably another reason for you to look us up. All of our membership and Discord and everything is up on the link tree.
Yeah.
Yep, the link tree. If you do have like 2 minutes though, please give that a scan. Let us know if you liked or didn't like anything. Obviously, we were running about half an hour late. Lines up, thank you guys. It lines up with how late we are. Due to some route changes that we've been out of control. But thankfully, everyone's all well. So that's all for today. Thanks so much for coming along. Next year.
Would like a recording of this is live stream so you can watch this again if you'd like, if you missed anything. Please feel free to take photos of any of the working out on the whiteboard. And also, if you haven't signed in, please sign in. Thank you very much. All right, thank you very much for everyone for attending to this, and please sign into the feedback forms and the sign-up sheets, and we'll be ending now. Thank you.